Welcome back. Today I'll interview David Peck. So let's jump right in. So, what do critical materials do in metals that make them so special?
Great question, Malta. Great question. The first thing is normally, not always, normally critical materials are an alloying element. So in other words, to give a different analogy, they're like the spices in food. They're not the main thing there, but without them, it doesn't work. And that's often the case with critical materials. And what do they actually do when we alloy them in? They make materials better under extreme conditions. And wind turbines, for example, often have to operate under extreme conditions. They make materials stronger, lighter. They make them corrosion resistant, more resistant to failure. That's very important for wind turbines. They last longer. They help the system produce more energy for the energy in, energy out type cycle. And in some cases, it's basically critical materials are just the best additional material to make the performance happen. So there's been decades, centuries even, of research, innovation, and experimentation to get us to the materials where we are. And engineers and material scientists, materials engineers, they put these materials in for a good reason. They don't put them in just because it might be nice. They put them in because it's really needed. And if they could avoid them, they would, because it adds cost and complexity, but they can't.
Okay, but what are the trade-offs if we have to substitute them for non-critical materials?
Non-critical materials, I love that. One of the challenges we have is what we've started to notice over recent decades is that where we substitute another element of the periodic table of elements, it is often still a critical material. It's just less critical than the one you're replacing. And that seems, okay, well, that's a step forwards, perhaps. But I wonder if the demand for that less critical material then goes up because you're substituting it, you end up back to square one. You suddenly got the same situation that you had in the first place where that material becomes more critical. And as I said before, the critical material is selected in the first place, as I said, often as an alloying element, because it is just simply the best choice. And the chances are, if you substitute for another one, you will make, as you suggested, trade-offs. So the performance will change, and in many cases go down slightly, or sometimes quite a lot. Now, whether you can manage that change or not is another question. But it's not like football players on a football field where you substitute one for another and you've got another good player on the field who's fresh and everything's great. It doesn't quite work like that with materials.
Also, sometimes it doesn't work like this in football.
It doesn't sometimes work like that in football either. That's quite true, yeah.
But okay, what about recycling? Couldn't we simply recycle all the materials that we need for wind turbines?
Yeah, wouldn't that be great?
Yeah.
Yeah, we just get all the old stuff, bring it all back, recycle it all, 100% of the material that we had in the first place, and then put it out there and generate power. Super closed loop cycle. And metals are great for recycling. They are a really good material to recycle. You can put them back into service again. But now there's the but. There's always a but, isn't there? Firstly, we're currently, thankfully in the world, increasing our renewable energy technology deployment. More and more stuff is being built. Wind turbines we're talking about this week. That is still growing in deployment, number of wind turbines, energy generating capacity of those wind turbines, size of the wind turbines. We see that all growing. And while you're in that rapid growth phase, even if you have some wind turbines coming out of service for recycling, it doesn't match the demand of the new ones you're building. That's a massive growth. So you've got this massive growth and this small number of wind turbines coming back. So we're a little bit out of sync. So perhaps by 2030, 2035, we'll start to see bigger numbers of wind turbines having completed a life cycle and coming back, and then we can start recycling. But that's not the whole story. So we've got this mismatch in timing and growth. Secondly, critical materials, depending on what critical material it is, but typically they're very technically difficult to recycle. To get that particular element out in a way that makes it useful to use again through a recycling process can be incredibly complex. And complexity adds to cost. It gets more and more and more expensive to get it out, till the point comes it's uneconomic to do so. Primary materials, mined materials, are way, way cheaper. So this recycling thing doesn't actually economically work. And then if we want to do that on scale, we also need recycling plants. And that includes metals processing. Often that's what we call smelting, remelting the metal into a new metal. And that requires energy. Now we're back around the loop again. All right, so we need to build new plants which require materials which need energy, and we need energy to run the plants. So we need more wind turbines. And there you start to see this is quite tricky. But we must do much more recycling. Going only for primary materials is not the way forward. So we need to mix it. So you can see recycled metals come with a lot of trade-offs and complexity that we're having to deal with.
Okay, but you mentioned timing. I heard in former times we made wind turbines without critical materials. Couldn't we do that again?
Yes, in a way, but let's just unpack that a little bit. So if we look at a material like steel or aluminium alloy, say for the tower or something like this, they contain critical materials. So really, we can't build any wind turbines without critical materials. But if we look at things, and we've been talking about the magnets in the generator, could we make a critical material-free magnet in the generator? Yes, because we used to do that, as you say, question mark. But that comes with a performance trade-off. The reason we started putting these elements like neodymium, dysprosium into magnets is because they massively increase the performance. Every turn of the blade, more power out. So if we go back to a design that doesn't have this, we're going to see a significant drop in energy production from the wind turbine. Now there's a solution to that, of course, increase the number of wind turbines. And then you go, yeah, but that's not very, So again, it's this trade-off where we've really got to think. Other areas in modern wind turbines, which we've already shown in some of the slides previously, are like the digital controller. That's full of critical materials. And modern wind turbines without a controller, they shut down. They should stop because they're dangerous and they won't perform properly. A better way forwards is to consider each critical material in turn, where we apply it, where we can try and reduce how much we use and keep the technical performance, where we can recycle, where we could extend the life of the wind turbines. And that can make a big difference. If we slow down our demand by designing new designs that are repairable, remanufacturable, that could give us real opportunities to begin to get in a balance with our critical material demand, our energy demand, number of wind turbines. We can start to get things in a bit more of a balance than the chaos we see right now.
Thank you.
Thanks very much, Martin.